Alright, so hello and welcome. Here we are with another problem. See if I can get a couple more in today before we move on to other things. Excuse me. Yeah, I don't know. I've been kind of conflicted lately about like what to do, what I should be doing. But I think we'll just get right into it. I mean, I've intended to solve these problems for a time. So here we are. We're loading the question now. So yeah, we'll just get right into it. We'll just keep going. I have a ways to go here. Distinct subsequences, 115, given two strings s and t, return the number of distinct subsequences of s which equals t. Oh, that's interesting. If a string subsequence is a new string formed from the original string by deleting some, can be none, of the characters without disturbing the remaining characters' relative positions, i.e. ace is a subsequence of a, b, c, d, e, while AEC is not. Is guaranteed the answer fits on a 32-bit signed integer. Okay. So S, we have 3. Rabbit, T is rabbit. As shown below, there are 3 ways you can generate rabbit from S. So R-A-B-B-I-T, R-A-B-B-I-T, and R-A-B-B-I-T. Yeah, so obviously this is combinatorial. The number of subsequences that you can have for a given string is very large. I think it's larger than exponential. It might just be exponential. Yeah, you can say, and the number of subsequences that are of a certain length, I think, is combinatorial. I want to say, I think that's right too. I could be wrong about that, but I think that's the case. You could include a character or not in your in a particular subsequence, and then for all of the subsequences that came before it, you can include the next character or not, right? And that's the inductive step. So by induction, you end up with, and that doubles, each character doubles the number of possible subsequences. Yes, I think that's the case. So yeah, so you can have, you can have an exponential number of subsequences, and therefore, and then the number of subsequences of a particular length, I believe it would be, basically that would be like n is the number of characters, and s, or we'll call it m, is the number of characters in the length of the subsequence. Then that's n choose m. You would have n choose m number of subsequences. So yeah, that could be combinatorially. The question though is, not only are you looking for subsequences of a certain length, which is n choose m, but also that have the specific sequence in T as well. So this should be an interesting question. Let's see if we can solve this. Shown below, there are 3 ways you can generate rabbit from S, bag, G bag, T is bag, bab, bab, G bag. Shown below, 5 ways you can generate bag from S, so B, A, G, B, A, G, B, A, G. Yeah, okay. And they're both going to be on the order of 1,000, consist of English letters. Okay. I think this is probably not too hard. Let's think about it for a minute, what it could be. Can't see. What could we do to solve this question? Let's ponder it for a moment. Let's think. So, now, okay, if this is combinatorial, and it could be, you know, a billion solutions, we want to compute these in pieces. We don't want to compute these in a way that's, what's the word? We want to compute this in pieces. We don't want to compute this in a way that is, we don't want to walk through every possibility, right? if we do an exhaustive search on every possibility, this could potentially take a very long time. As I said, it's combinatorial. So that could be too expensive, right? So we do want to reduce this down to like it's a counting problem, right? We want to try to count this more efficiently than a pure exhaustive search. Okay, well, maybe we could do this in a way that's memoized, something like that. Maybe we can just use a depth first search and memoize it. Maybe that's possible. It's very likely we could do that. Excuse me, and summate and perform summations over memoized values. I could do it. Let's think about that. So let's say we had a certain number of ways that we could set up. Let's say a certain number of ways. Well, since these are left to right, maybe it's better we go right to left. So we could say, how many ways can we get rabbi? How many ways can we get r? Start with that. There's one way. And then of those ways that we can get r, how many ways can we get RA, right? And then from there, RAB, RABB, RABBIT, right? Maybe that's one way to memorize. I think actually it's probably better if we just try to do like just a simple depth first search and think if there's some way to memorize that. That's probably easier than trying to think that through what I just described. So yeah, so we'll just try a naive approach. Okay, so exhaustive search would be what? We would say we could start our subsequence at a given point. And we would say if this is a character that begins the string that we're looking for, then we can increment the pattern that we're looking for, right? And also, so we included this character. So actually, this is very similar to just memoizing an exponential. Like in other words, your subsequence could include this character or not. This might not be that difficult. So we have some subsequences, right? We can say, so we have two indices, right? The first string and the second string. If the character matches these characters match, then we can include in the subsequence. We also can skip, so we can add both. If it doesn't match, then we must skip. We can't include both. But you have sort of a returned value. Returned sum would be the sum of all of the subsequences where you included R and all of the subsequences where you did not include R, or include that position or not include. I think it's actually like really straightforward to do this. Yeah, this might be like a really easy one comparatively. Like this might be a lot easier than I realize. How are we doing on time? So yeah, 8 minutes in. Okay. So let's try this. We're going to probably memorize this. So we'll come back to that in a moment. And we'll convert this to a DFS as well, to a probably memorize this, and then also we can convert this to a dynamic programming solution shortly thereafter as well. So I kind of already know. I think I already know what this is going to look like. So we'll give it a shot. Also DFS. It's always just DFS over and over again. Int I, or we could do A and B. I prefer A and B. B, F, memo as well. Return 0, 0, dfs, and we say base cases if b is greater than or equal to t dot size, then return 1. Auto key is going to be standard make tuple of s and or a and b. If memo.count of key, then we can say return memo of key. And we're going to say, so if int ret equals 0, something like this I should do the trick, I think. So we say if memo of key equals ret, return ret. If s of a is equal to t of b, then we can add to ret recursively, and we're going to say we can increment a and we can increment b. Right, we can increment both characters and find the result. So the number of subsequences, if we move the pattern forward one character and also move the string that we're operating on one character, and then also you can always move the character forward without moving the pattern forward. And that's pretty much it. I think that's it. I think that'll give you everything you need. This is not super efficient though, by the way. This is actually no, I think this is quadratic. I think this is quadratic time algorithm. Oh, we got a runtime error, no kidding. Okay. Stack buffer overflow. Oh, that's interesting. Interesting. Oh, I know. So if you go over the edge on A, you return 0. There you go. I think that's a correct solution. Not the most efficient though. Can we use some other? I don't know. Let's try some of these. Okay. 1 and 0. That's interesting. I think this might work in general. Only 1, huh? Let's do something like a little crazy. How about that? That should have a lot. That should be my TLE. Okay, still 0 milliseconds. Okay, now we're gonna pull out our handy dandy test case generator and see if we could break this. Because I think this code should break in some cases. Actually, we could just do, I don't know, we could do like AB 1,000 times, something like that. X could be nothing, and then we could just do a for loop of I equals 0, I is less than 1,000, plus plus I, and we'll say X is equal to itself, concatenated with AB. So we'll actually do 500 instead of 1,000. Alrighty, and I don't know, we'll do like AB a bunch of times. Something like this. That's relatively efficient. Let's do AB a few more times. See what that gives us. I think this breaks in some. I see. Nice. It's a lot. So, as I was saying, it's combinatorial, so there are a lot. I don't actually know. What if we just make everything longs? Long. Well, if everything's gonna fit in an integer, then I think we're fine. I don't know. I think we just go for it. I don't know. It's probably wrong. Oh, we got it. Hey. Nice. There you go. How long did that take? 17 minutes? Can we just on the next one? Do we just close it there? I don't know, man. I don't know. Not bad, but yeah. Well, this test case broke. Being only in a 32-bit integer kind of makes it like it's probably doable in oh wow, dude, that got really big really fast. Probably doable in just simple code like this. Yeah, that's a lot. 1,000 shoes, like 3 or 4 is just a lot. Looks like you really can't go more than 2 here, huh? 1,000 choose 3. There you go. Okay. So anyway, yeah. All right. That's efficient enough. There's got to be a way to do this that's faster. I think algorithmically it's got to be better than this. This is actually pretty slow. This is quadratic. Can you do better than quadratic? I guess you probably could. Hi mate. Hey, hello Melito. Well, we just finished the problem. How you doing? We made pretty good time too. We made oops. Oh, didn't mean to do that. Made, less than 20 minutes here. But the question is okay, sure, I say I've solved it in 20 minutes, but how do I could optimize this using using dynamic programming, but there's got to be a more efficient algorithm. Right? This is way too slow compared to what other people have. Can we? Well, it'll be like 10 times faster if we use dynamic programming, right? So let's try that. Let's give that a shot. So we could say. So yeah, this is super quick to code. That's kind of what I was saying before. It's like it's very fast to code something using recursion like this. But let's try the DP version. So let's have an array of integers, and we're going to have int m and n, I suppose, or a and or yeah, we'll do m and n. M is s dot size. And n is, these are constants, right? These don't change. and n is t dot size, and we'll say m by n of integers, and it's unfortunately we don't have a way to initialize this. Don't have a way to initialize these variable arrays, so we have, it's a bit awkward, but it's okay. Initialize to 0. And now we're going to say we're going to go upwards, so we're going to say for each, or not upwards actually, we're going to start with the bottom, right? So the bottom is the back. So we're going to go back to front. Yeah, let's practice our dynamic programming solution here. So 0, 0, right? So we're going to back to front, and we're going to say in the back we're going to start initial state. So this is setting up the data structure. Let's say the initial value. And then we're going to say dp. So the initial value is going to be from the back. I'm going to set some of these to 1 and some of them not to 1. Some of these will start off at 0. So actually the back is exactly when the last character of the pattern meets one of the characters of the, so that might not be true. This might actually work to DP this. The DP is a lot more challenging in my opinion. That's the thing I'm kind of struggling with, is converting from memoized recursion to dynamic programming solutions. I struggle with that. So if the last character of the pattern is now, no, this should go, I think I'm doing it wrong actually. I'm not sure. How can we do this in a way of using dynamic programming? So this is quadratic time complexity, and this is also we're adding numbers together. We have 0 if we're over the size, right? But we haven't gotten to the end of the pattern. So everywhere that we're at the end of the pattern, we have a 1. Yeah, and the tricky thing about that is we assume that if we ever get to that point, yeah, we can do it. I think we could do it that way. So this is kind of weird, but we assume that if we could ever get to the end of the array, that would have a 1 in it. So everything has 0 except for that. So let's go to for each possible value of it's really going to be for each value of a. There's an initial state. So each value of a is less than m and plus a. We're going to say array of a of, now this is going to be the last one. So I think we greater than or equal to, we add 1. So we could do b plus 1. So n plus 1 we could say. Could do it that way. That's probably better. Less than or equal to n. And we're actually going to say, oh no, the other way around. m n, no, we're fine, we're doing it right. This is okay. Of n is equal to 1. Okay, I think this works. And now we're going to say from back to front, we're going to say for does this make sense? I don't know if this makes any sense. Starting from B in the back and moving forwards, I don't think this makes sense the way I'm trying to do this. I don't think this makes sense the way I'm trying to do it. I don't think so. I don't think so. Excuse me. Could try something like this. I don't think it works. So these are all zeros. These are all ones. When they're both through the pattern, they're ones. So the idea is that if at any point you get through the pattern, then any value of a, that'll be set to 1. Yeah, that makes sense. And what you want to do is all those instances where you got through the pattern, you're going to go backwards and either add or not add to the point right before that, depending on whether or not you can add this character to the sequence or the pattern or not. Okay, interesting. So let's try to calculate this. I think we start at the back with, I think both of these start at the back. That's the thing I'm not sure about. It's a little weird. It's a little weird. So, okay. So, going backwards, we'll start with, I think we calculate for each A. Is that what we do? Yeah, I think we calculate each A. So int A equals, starts off with, as n, it starts off with n minus 1. A is greater than or equal to 0, decrement A. And B equals m minus 1. B is greater than or equal to 0, decrement B. And you're going to say array of A, B is going to be plus equals so you have two things. You say if S of A equals T of B, then you can include the array plus 1, B plus 1 values. And in all other cases, you can include array of a plus 1b values. I don't think this is correct, though. I don't think this works. I don't think this gives us the right answer. I think there's something wrong about this. A is M and B is N. L, M, N. That's my mistake. Something like this. Oh, not only is it correct, but it's efficient. Is it correct? I don't. This doesn't seem right. Okay. Oh, what happened? All right, that's interesting. Huh. Can make these longs. Oh, it's still correct. Do you pay to run this app? No. You mean LeetCode? Like using LeetCode? Oh man. Brother. That's so funny. What? It's huge. It's too big. So it looks like we're using a lot of data we don't need to use, I guess, because these numbers are too big even to fit a long. We need to use a big integer for these. We could do this. I think this is. I think this works. This is gigantic though. These numbers. This is the largest possible number you could put. Oh, there we go. Hey. Oh, okay. Whoa. That's pretty simple. Yes, LeetCode. I used to, yeah, way back when. I don't anymore. When I was younger, maybe 4 or 5 years ago, I paid for it. I had a subscription for years, but I turned that off because one, I've got thousands of problems to go through, and two, also it's expensive. Yeah, it's not cheap. So I like LeetCode, and I don't have a job. Once I get a job, like once I make it pretty good money, I'll probably have a subscription again, just because I'm really grateful for what LeetCode has done for me, and how much time I use and all that. So this is kind of bewildering, but it looks like the idea that I had of just like going back to front. So this is top down and this is bottom up. It looks like the bottom up approach was actually as simple as I thought it might be. Just go backwards and start from like if you are able to get all the way through the pattern. The tricky thing about this though, the only problem is that obviously in our array we end up having numbers that are very large because we're calculating like intermediate pieces, I suppose, and those end up being very big. Interesting, couple things interesting. First off, that this is only 70% speed. That actually there's some other solutions that were much better than this, 65%. This wasn't even the fastest. That's one thing. And the second thing is, yeah, I guess if we can get to like 8 milliseconds or something. We're using a little bit more memory than we should, though, I suppose. I guess I guess there's a lot of pieces here that we could skip that I'm missing. I'm not realizing. But yeah, that's a lot faster, right? That's almost 20 times faster, quite a bit 10 times faster, quite a bit faster, 100 times faster. It's like a lot faster. It's almost 100. Yeah, it's almost 100 times faster doing it this way rather than the way I was doing it before. Thank you for asking, by the way, Melito. But yeah, obviously the DP approach is just a lot more efficient. I don't know. The runtime is not great. It's quadratic runtime. It's not phenomenal. But yeah, I mean, there's just a lot of extra like machinery going on here when you do it this way. So I guess that's why it's so much faster. But I guess, yeah, I mean, this is fine. You know, we did get it in 12 milliseconds, so it's pretty quick. I just don't like that I'm doing it this way where I'm storing such large numbers in between. Like, I'm wondering if I should, like I should just add like a check in here to see if adding this value would exceed this amount, then excuse me, then just don't add, because there's a lot of information here that can get just kind of tossed out. Like I think there's a lot of redundant information that's being used here. Yeah, there must be a way to do this that's actually better than quadratic. I think that's probably how people got it down to even faster. Pretty interesting though that these conditions, you pretty much could just start from the back, go to the front. I couldn't think that through though, like the logic, like that's super not obvious to me at all that works. Because I would think like if you can make it all the way through the pattern, then I think that's the deal. I think that you don't get all the way through the pattern to get to this point. Because if you don't, that's why. Okay, yeah, because if you don't decrement B, right? So you see this one, this is a 0, and if you add a 0 to it, it'll just stay at 0. So if you never get all the way through the pattern, then all those things you added don't get appended. So that is a lot of extra computation though, a lot of numbers that are just unused here. So we could go back to an integer and we just say anything that goes over an integer is just going to be tossed out. So that's really interesting. It was kind of a lesson I learned here, is that still here. Hey, welcome back. Yeah, so I did learn something here. One, you can actually just go bottom up, and sometimes it is that simple. It's not as intuitive, but it's often just as simple as just going backwards. And then the other thing is, so yeah, there actually is kind of a simple, usually simple, not the most obvious or simple, but it's not necessarily obvious, but there's probably a simple way to convert from top down to bottom up. And then also, maybe it can be really hard sometimes, but it shouldn't always be that difficult. That's one thing. And then two, when you convert to DP, you might end up calculating numbers that are too large, that never make it to the final calculation, and those you could just toss those out. So what we can do, so we can remove tuple and map, and we can go to numeric. And then we can say, so we just add an if statement here, a guard, and say if, so standard numeric int max, if that minus this amount is, so basically we want to say x plus y is less than or equal to int max, or max, yeah, int max. So that's another way of expressing that is that int max minus y is greater than or equal to x, or x is less than or equal to int max minus y. So we can say if x, which is array of a, b, is less than or equal to this int max minus what we're about to add to it, and we're going to say, and it's got to be greater than. So and the negation of that end is greater than this difference. Right, we can add this guard. So if as long as this is greater than this difference, actually it's going to be less than or equal to that difference. I did that wrong. We want it to be less than or equal to. So if it's greater than, so we want not greater than. So we want, yeah, okay, that's confusing. But I appreciate that, Melito. I appreciate you spending some time with me. I'm grateful. I don't know how much you like computer programming, but that's like all I'm doing as of late. But yeah, so if this is the case and this is less than or equal to max, then we can go there. And then we have another guard here too. So we say if this is the case. So this allows us to keep our values where they need to be. Okay. And this one's just a plus b. So this allows us to keep us in the realm of like not calculating numbers that are too large. I think this will work too. This I think is faster. Oh, didn't mean to keep that. So yeah, I learned something. Oh, I think it's numeric limits or limits. It's actually not numeric. It's actually limits, I think, or is it just limits? I don't remember. Limits, numeric limits. Okay, I did it wrong. It's not numeric, it's limits, numeric limits. Okay, let's try that. Let's see if this works. Okay, and we got the very large one. Now is this faster or slower? Not much faster. A little bit better on memory. Yeah, see, we're not storing all these gigantic numbers in memory anymore. Yeah, we can kind of terminate early on these ones. So I mean, not as fast as it could be though. Would have gotten into programming, but I'm busy in other things. Yeah, I could see that. That's fair. Me too. Well, actually, yeah, I wouldn't say me too. I'd say like, yeah, it's all consuming for me as a developer. It's like my whole life. It's just this. Program. Learn to program. Learn to code. You must learn to code. You must learn to code. I honestly, not honestly, I would say, dishonestly say, I would say it's not worth becoming a programmer. Like some guys do really well, but it's sort of like 1 in a million, and like you kind of have to embrace evil to do really well anyway. Like you're better off just getting some other job, I think. Programming is just way too exhausting in terms of All right, I don't know why I can't get faster than this. I think it's the best I got, but this is pretty good. I mean, this is better memory than we just had. Well, it's not as fast as what we just had, so I actually think I'd prefer the other one. I think I'd prefer this one, and we'll just keep it simple. Yeah, basically this size t means it's like a variable size number. It's pretty much as large an integer as it will fit into memory. It's pretty much what it says, which is pretty big. It's a pretty big piece of memory. Pretty big piece of, yeah. Yeah, I think it's slightly less efficient on memory to do it this way, but we were able to get a slightly faster approach though, because we don't have the other branch here. I mean, I don't know, like what else can we do here? Let's look at the discussion. Easy to understand DP in Java, 7 to 10 solutions, detailed explanations. Better solution takes less than O(n) space, O(n) time. I don't think so. DP clarification. Question should be reworded. 7 to 10 lines. I think mine was like 7 to 10 lines too. Oh yeah, because you can put it on one line. You can make the DP vector of vectors. Yeah, and also the ternary operator. I might do the same thing here. This is pretty much what I did. It's just a fewer lines of code with this. Although I went backwards, you went forwards. I think it's easier to think about it going backwards, but I don't know. It's fine. It might be actually more efficient to go forwards though instead of going backwards. Maybe? I don't know. I don't think so. Oh, whoops. I forgot about that part. Yeah, you can optimize the space a little bit here. So I totally forgot about that. Yeah, you can this part you can optimize. That's what he does. That's a few more lines. I completely forgot. Completely forgot you can optimize the space a little bit better. Yeah, you can use it. Oh, that's probably what. Oh, that's the optimization. Oh, I completely messed up. I forgot. Oh dear. I forgot. No! Oh! We'll add that in a moment. I totally forgot to do that. That's really funny. Yeah, you could do better space time. Space complexity. I totally missed it. I goofed. Clarify problem. Sync subsequences of t and see how many of any pair has. Is that equal to 3 in the given example? No. All right. Yeah. What? Totally 3. Oh, this might have been before. They may have clarified the question. Yeah. Okay. Thank you for Miss Maja for clarifying that. Well, there's one way to do less memory, but runtime is hard to improve, I think, on this one. Anyway, all right. Well, I actually, it's really funny too. Not funny, but like what's frustrating about this is that I actually knew that you could use less memory. It's only one loop here. It's super simple. It's just this inner loop here. You just make this this array of b and array of a plus 1 b plus 1. It's okay. So we're going to use a vector for b. That's the one. So that's doesn't need to be an array. We don't need this array. We just need array of n plus 1. And then we can just say, yeah, optimizing the memory for this is super simple. So we would say array of j, right? And then now we have initial value. Oh, that's tricky. Oh, actually, maybe I'm wrong. Maybe it's not as easy as I thought. Oh, yeah, if we go backwards, then it's not as easy. I think I have to go forwards. You lost something? I heard you screaming. Yeah, I made a mistake. There's a pretty simple way to improve this algorithm, and I missed it. I made a mistake. I think though, yeah, the way you would do this, you could use two arrays, I think. So you have array, and then you have next array. Right? And what you're going to do is both of these are 0. I could be wrong about this, actually. This might not be as easy as I thought. Initial value is going to set our array to 1. All of these go to 1. So not quite correct, actually. No. Basically, you perform this first iteration on an array. Let's do that. So the first iteration says array of A plus 1, B plus 1. So this is the current array, and this is going to be the next array, and this is the current array. So the next array is 0, and you're going to add to it the current array. Right, this will be the current array. This would be B plus 1. So actually, what you can do is like easier than you could walk through it rather than trying to think it out. Like we can hold on. Let's see. Let me do this in a better way. Okay, let's just make sure it's still correct. We can walk through this to improve the memory. That's what I forgot to do. I was supposed to do that. Like, this is the kind of thing that you'd want to ideally be able to do like kind of quickly, but walking through it a few times. So we'll say current array n plus 1, and then another array, which is next array n plus 1. Right? Excuse me. And you can take this loop, and you could set the current array and the next array to 0. Right? Now the current array actually should be 1s, I think, and the next array should be 0s. Okay, I'll explain what we're going to do. So we set our initial values. Initial value. And what we're going to do is, in this loop, if this is the case, we're going to take the array, the current array, or the next array of B is going to be plus equals the current array of B plus 1. And the next array of B plus equals the current array of just B. Right? So you have current array of B, next array of A of B equals current array. Anyways, I'm leaving. See you later. All right, take care, Melito. Talk to you soon. It was good to see you. I appreciate you coming by and saying hello. Talk to you soon. Enjoy the rest of your day. All right, so next array is going to be current array of B. So this is B plus 1 and this is B. And what you can say now is then you can update the you can, so current array gets updated to, so next array becomes the sum of the current array, right? And now you want to set the current array equal to the next array. We could use I, we should use I. So we're going to say, now the current array gets updated to the next array. We basically swap our arrays, and then update the next array to 0. Right. And then we're going to say return array 0. Also, we can return array current array of 0. Something like this ought to work too. Now this is just like a translation. This is the kind of translation that you probably would want to be able to do programmatically. This is in B, this is I now. Oops. Whoa. Yeah, I completely forgot. This is the kind of translation that the logic is kind of straightforward, but it's not so obvious to see how to do this. Okay, now we can go, let's try this one. Do we get the same answer? I think we should. Oh, it's wrong. Oh no. Okay. It's A plus 1, and this is A plus 1. This is the current array. Now, current array starts off at A of n. All these values of n have 1. So I think there's only one value at, I think this is not true. I think these are both 0. And then I think there's only one value here when A is m. So mn, so we just say current array of mn is 1, but that's just m. So it's just, I think that's what it's supposed to be. I think I had it wrong. Yeah. Oh, 1, 2, 3, 4, 5, 6. Wrong answer. Oof. Oof. Not quite. Not quite the right answer. Really? Oh. I think the next array is always a 1. Or the... starts off with a 1. And then... oh no. It's wrong. I'm wrong. No. No. Should this always be a 1? Maybe that's what I'm missing. Current array of n should always be 1. Maybe that's the issue. I don't know. Oh. Huh. I lost my test cases. Oh, here we go. Can use these. Okay. How are we doing? Hey, that looks correct. Let's see. Are we still correct? All right, there we go. So we've reduced the amount of memory we need. So now we can get rid of this array altogether. There you go. There. How's that for an optimization on memory? How's that for memory optimization? There you go. There you go. 98. That's what I like to see. That's what I like to see. A lot less memory. However, we're not yet optimal on the time. So using less memory obviously uses less time to allocate the memory and to run each operation, right? You're just doing less overall. But the question is, how do we set this up properly? So this is how we go from one array to the next, right? We just basically just have two arrays, and you do all your operations on one array, and then copy that into another array, and then swap the buffers, right? That's basically the basic way you can, if you have a dynamic programming solution and you want to reduce the amount of memory you're using, if you're just running an inner loop, you can just have like two buffers, one buffer of the previous result, next buffer of the next result, and then just swap those buffers. That's sort of what we're doing at each step here. The question though is whether or not you even need to do that. I don't know that you do. So what's interesting is that your array is always going to remain the same at every step. And in some instances you can increment your spot. So actually we can even go further and make this even more efficient by using one array. You ready for this? So we could say sometimes you don't actually need two buffers. Ready for this one? We should use I think. So we're going to zero out this array, and now we're going to set the last value to 1, and then we're going to go ahead and DP. We're going to copy this. Okay. Whew. So this is array plus equals this other array itself, and this actually becomes just doesn't get touched, right? So in some cases we'll add, and we're going to go backwards. So now what's tricky about this is you're adding the one in front. So actually you want to go forwards. You don't want to go backwards. You can just reverse this loop. So yeah. So what's tricky here is that so the way that I had set things up, you can use the double swap buffer, and that works, but you can also reverse how you're processing the array, so that way you can just use a single array. Because because what we're doing now is we're going backwards, but we're adding from in front of us, right? Which is a problem, because if you change the thing you change some value x, and you process x minus 1, but it's gonna add the changed value, which is what you don't want to do. So we want to actually go the other direction. We want to go from b equals 0 to I'll explain how that works. So b equals 0 to n n and increment b. And now what's going to happen is if these things are equal to each other, then array of b plus equals, I think you can do the same thing, just now in the other direction. So array of b plus 1. Yeah. And you always add it to itself, so it always gets updated. So we can do that. And so we don't really need these anymore, do we? We don't need to update this either, this current array n, because we're never going to touch it either. And so now you can say just array of 0 at the end of all that computing. And so I think you can just use one array for this too. And I think that works. Let's go for it. See how we do. Hey, there we go. There's that 90% that we're looking for. Sweet. All right, now let's get rid of all the other code that we had. So there you go. So that's the memoized quadratic memory, quadratic runtime. But if you want to optimize the memory usage, then you probably want to switch from, that's top down, you switch from top down to bottom up, and then you can, I think you could still technically do top down with less memory. I guess it would be like still like a dynamic programming kind of approach. It'd be like a BFS rather than a DFS. But yeah, so you could still do, yeah, you could still optimize this using something that's not, well, you still could probably optimize the memory without necessarily going to DP, but I think it's a little bit easier to understand how to optimize when you're using DP. And yeah, so we don't need any of this anymore. Just have an array, have m and n. You don't really need m. Oh, you do have m, yeah. Super concise. So that would be my solution to this problem. Took us an hour to go through the whole thing, but that's pretty good. 8 milliseconds is not too bad. We're not quite 100%, but we're pretty fast. We are overall pretty fast. I don't know. Can you do fast than this with even less memory than this? It's kind of uncertain to me if that's even possible. Oh, we got 100% memory. That's pretty good. So somehow you can do this a little bit faster. Maybe array of b plus equals itself. Maybe if you use pointers to do this rather than indices, that might be a little bit faster. Actually, that's probably faster. So we can say S of A, D of B. If you were to say we could try to use pointers here to make it a little bit faster. I don't know about that. Oh no, well, we need B though. You could do, I mean, you could do like, I don't know if there's a way to make this faster, quite frankly. This is all I got. This is really all I got. So you do S begin, and then T begin. Yeah, I don't know if it's going to be much faster. Probably not. Another question is whether or not this would be like whether or not you can optimize the memory even further. I don't think so. That's interesting. No matching function for call to begin. Can't be used as a template assignment. For whatever reason, that's just not working. I don't know what's going on there, but it's just not working. I don't know. I couldn't tell you. We'll go back though. What we had. I guess one optimization would be to one question is if we use integers. It does give runtime error. Well, you could also do, and we were saying it's array of B is less than or equal to standard numeric limits of integers maximum minus array of B plus 1. Right? Let's see. Okay, that's the correct answer. I don't think it's faster though. Oh, it is. Hey, look at that. Huzzah. Yeah, because we do less calculating if we add this. How you like that? How you like that? Ah, there we go. There we go. Sweet. So somebody somehow ended up getting this, somehow got this down to 0 milliseconds, I think. I guess you'd have to just keep running it over and over until you get 0 milliseconds. I don't know. I don't know how you get this down to 0 milliseconds. But we're doing pretty good on the memory. I think actually we're doing better. Well, I don't know. It is slightly less memory if we use well, apparently it's less memory if we don't use ints. I don't know why that would be. It's not much faster we do this actually. We probably should just go back to what we did before. I think what we did before is better. It's easier to think about. I like this one better. Yeah, these size t's are basically like infinite sized integers. There we go. Okay, it's kind of random whether or not what we get. So sometimes we get 94 milliseconds. Okay. I don't know. Somebody somehow got 0 milliseconds on this. But yeah, DP solutions are pretty fast. Potentially very fast, depending on how you do them. Usually you're looking for the asymptotic time complexity, but with code it does matter if you get the sort of fastest. So yeah, this is this solution is due to you take the memoized version, then you convert that to a bottom-up approach, dynamic programming approach. Excuse me, then you optimize the dynamic programming approach around memory, and that gives you pretty fast runtime. So yeah, we're like 1,000 times faster, not 1,000 times faster, but like 100, over 100, couple hundred times faster, about 100 times faster. That's good. That's good. Being 100 times faster is good. All right, I'm gonna end it here. Thank you for watching. This is the kind of thing that I can really get sucked into, but it's something I kind of need to practice. A lot of the hard problems have that element to it of like optimizing loops to make to use dynamic programming solutions rather than like memoized solutions, and I find it very challenging. I struggle from time to time. But yeah, thank you for watching. It's been fun. It's been interesting. I don't know what I'm doing now. I might take another break for some time. But this is one of those things where, like, if I can get that right, you know, then every time I see a problem similar to this, it's sort of a dynamic programming question that could be optimized, then I could just optimize it like out the gate, come up with a solution and optimization very quickly, and just kind of go one to the next. And I solved this pretty quick. This is like 20 minutes I solved it. So, I mean, if I get to the point where I'm solving these like 4 problems an hour, I could probably get to the point where I'm solving these problems like 10 minutes a problem, and also get like the super fast DP solution. And then if we could do like 5 minutes a problem, then we're looking at like 12 problems per hour. Or sorry, 10 minutes a problem is like 6 problems per hour, and that's like 70 problems per day. And basically in like a month, I could solve the whole LeetCode sort of library here, which I think we're okay at this point. Like I think I'm there as far as like these sorts of problems. I think like I could solve them very quickly now. They do get kind of repetitive after a while. Obviously, there's like a lot of stuff I needed to practice. Kind of just need to like spend the time practicing. I do kind of waste a lot of time just thinking about stuff, which I think is okay. But like, I don't know. It's like, I don't know. But yeah. So pretty interesting. Like that wasn't too bad. That was all right. A lot of problems are kind of similar. Yeah, we'll just keep going. I guess, I don't know. Like I said, I think I'll stop here. Say thank you again. Talk to you soon. And I don't know what I'm doing next. Probably just take a break for a while. Just kind of relax. I might just pick up another problem too. I'll decide what I want to do. But yeah, thank you again.